overall. All right. Essentially, what we're going to be is networks and internet working. We're going to be looking at what are different reference models, how internet applications works, all right, certain standards that are used within data communications, all right. We're also going to be talking about the various different functions of the different layers that are adopted by several different communication protocols, all right, especially the transport layer and the internet layer. And we're also going to be talking about something known as subnetting. So today is going to be more of an introductory into the subject overall. All right. So we're going to be looking at various different definitions so that we can get a better handling of what we're actually going to be talking about throughout these sessions that we have together. So first and foremost, so let's get started. So if we take a look at the term telecommunication, basically, telecommunication literally means communicating from afar. All right. In fact, the word tele, all right, literally means far. All right. And this is something that has been around with us for eons. We've wanted to be able to communicate far and wide, all right, in order to be able to get our communication or our messages out to other people as quickly as possible. All right, and this does not necessarily mean, all right, that it has to be in a digital format. All right, it's been going back centuries. All right, forms of communication from afar include, waving flags, beacons, carrier pigeons, smoke signals. All right, and so on and so forth. The idea is to be able to transport a message from the sender to the receiver. All right. Um, and as I said, these have been around since antiquity. All right, even in Malta, we have coastal towers that are used in order to protect our border. But it's not only just in order to protect our inlets or our bays. Essentially, they were also used as a communication device in order to inform the local populace. Listen, we're under attack. Essentially, you send smoke signals or fire signals from one tower to the next, and essentially that message of warning propagates throughout the country very, very, very quickly. All right, this is not only unique to Malta. Even on the Great Wall of China, they use this. All right, and in fact, most of China could actually get or get informed that something was amiss at their border, given the size of China. It's quite um, uh, it's quite understandable that you would want to have this information, but they've calculated that it can actually take a few minutes in order to just um, state that one is under attack or something of the sort. So in our case, what we really are interested in is how we communicate, all right, data, okay, with others, all right. Particularly, we're going to be talking about how data is going to be exchanged between two different devices via some form of medium. And we're going to be expressing what goes on in a step-by-step manner from these two, from sender to receiver, all right, via the different types of communications that one might make use of, or different types of mediums that one might make use of in order to understand, all right, how communication is actually possible. But before we actually delve into, all right, current technology and to see how these different devices work, we're going to look back all right, in order to see where the foundations of modern day communication systems start from, all right, by looking at some important innovations that have happened throughout the years, all right. And the very first innovation that we're going to be talking about, all right, is that developed by Samuel Morse, all right, also known as the Morse code, all right. It's still technically speaking being used today, all right, even for cross um, ship to ship communication, all right, via light flashes. All right, you probably have seen certain devices like this, even in period films such as, I don't know, Titanic and so on and so forth. All right, where essentially um, the alphabet, all right, the international Morse code alphabet was broken down into individual characters, where each character was represented by a series of dots and dashes. All right, and you probably would have heard these different interpretations of these dots and dashes. All right, you know, essentially reading those dots and dashes in sequence will give you one understanding of what the message happens to be um, to be delivered. All right, and um, this is one of the more important, if you will, um, um, innovations that has actually propelled communication forward quite a lot. In fact, it changed it changed the way how information was actually sent from one country to the next as well, because essentially the speed at which Morse code actually travels is actually the speed of light, which is by, by far faster than, say, travel or messages delivered via, I don't know, letters, you know, pre-written letters. Um, in fact, if one was to produce some news, all right, and transport it from one side of, I don't know, let's say America to the other, all right. Before it used to take days, literally days, in order, if not months, for that piece of information or for that piece of news to arrive at its destination, all right. With something like the Morse code, all right, it actually brought the world closer together because people knew about current events pretty much as they happened. All right, I mentioned the Titanic, for example. All right, the news that the Titanic has sunk literally reached the entire Western world. All right, pretty much the day after it sank. You know, everybody knew that the Titanic had sunk, thanks in no small part to the Morse code. Okay. Um, uh, Another invention, all right, is something that we currently use a lot even today. That is that of the telephone. All right, the very earliest telephone invented in 1976 or thereabouts by Alexander Graham Bell. Um, was another step forward in the sense that it allowed two people to communicate with each other using their own voice. All right. So you had two-way communication at both the sender and the receiver actually sending down voice signals down an electrical wire. All right. In order to allow such communications. In fact, um, um, such telephones have actually also paved the way, all right, for the internet and the fact that we actually are talking together here on this channel. Yeah, we're actually making use of even um, um, certain notions, even certain conceived infrastructures that were put originally for telephony. All right. So, in fact, we're actually going to be talking about how the internet actually exists and predominantly exists because of the infrastructure put forward for telephony. All right. Another great invention, invented in 1869, all right, was developed by Guillermo Marconi. All right. Guillermo Marconi basically invented the radio, in which one could actually send signals from one device to another completely wirelessly. All right. And that also paves the way to some of the wireless technologies that we still use today. Essentially, wireless, anything that works in a wireless fashion uses radio waves, which were first and foremost um, uh, not invented but discovered, and the invention was how to make use of those radio waves in order to be able to send signals from one device to the other. All right, and obviously decrypt them or decipher them and play them back so that they actually make sense. They do so. It's the conversion, if you will, of um, of signals. All right, from something which we might understand. So, for example, I if you're listening to the radio, for example, you'd have your radio DJ talking on a microphone. All right, so that would be an analog signal. All right, it was being captured by the microphone. The microphone then um, captures that sound and converts it into a digital format. It then is broadcast, all right, using radio towers. It is then received by your radio, assuming that you're tuned to that particular device, um, and converted back into an oral sound that you can understand. All right, so that is essentially the invention that was put forward by Marconi. All right. Moving forward, all right, in 1890, all right, you get Thomas Edison, who invented or found a way rather to showcase moving pictures amongst other inventions that Thomas Edison is famous for. All right, essentially, he gave rise to the notion of the movie theater. Essentially, all right, being able to showcase a sequence or a series of of images, all right, one after the other, all slightly different from one another, in order to give us the perception, the illusion of motion. Okay, um, and that in turn led to another invention, all right, which was developed by John Logie Baird, all right, in 1925, who actually transmitted those moving pictures over um, over a particular wireless signal. Therefore, one gets the invention of TV signals. Over here, you can actually see, all right, the very first face, all right, that was actually transmitted using this television idea. All right. Obviously, there have been a lot more developments. All right, you get, for example, the development of mainframes, which are accessed via the use of terminals. So essentially, what you get is these terminals, all right, these dummy end users making use of the resources provided by the mainframe, and therefore one would actually need to have a local area network, all right, so the development of the local area network comes along so that one can actually connect, all right, a terminal with a mainframe in order to make use of those resources. Obviously, uh, these lands, all right, um, also led to the invention, all right, of certain standards which are used in data communication nowadays. All right. In fact, we now have moved on to using pretty much standard systems of communication in order to help. All right. To help how these communicate, or how these devices can actually communicate with each other. If you think about it, all right. Um, uh, Today, all right, now, all right, each and every one of you has their own machine, all right. Their own machine is connected in some way, shape, or form to a router. That router in turn is connected probably to a modem. That modem in turn is connected to your ISP. Your ISP might be completely different from the ISP that I have. So somehow there is a connection between those two ISPs. All right. That signal is coming back. All right. To my to my router to my modem, from my modem into my computer. All right. So any signal that you are sending to me, all right, is going through all of these different devices. But somehow they're all communicating with each other. All right. No matter what, even no matter what kind of device you have. Um, what the make was, all right, how old it is, all right. Some people have older devices than others, but they all use similar protocols and similar systems and similar standards, all right, which allow these different devices to communicate with one another. If you think about it in that sense, all right, you can start to appreciate how um, how complicated, all right, a piece of communication can actually be if it were not for these standards. All right. In fact, that is why we actually have this form of communication that we can actually have today, because we actually have these standards. Obviously, having and network computers led to yet other innovations, such as the innovation of electronic mail, all right, being able to send messages between one computer and the next. At first, between one computer and the next on the same network, and then um, over different networks using the internet. All right, maybe being able to have remote access or remote backups, and so on and so forth. So any form um, um, of internet service or network service that you might think of has been a direct development. All right, because we actually have um, um, computers connected together in networks. All right, and it allows for one in order um, um, to make use, all right, of or make better use of these systems in order to make our lives obviously a lot more interesting. Now, obviously, there are different types of communication. All right, so we have what is known as one-way, all right, communication or linear communication. We also have what is known as two-way communication, all right, which is more interactional, all right, something which requires an element of feedback, all right. And then you also have what is known as your transactional communication, all right. So having this in mind, all right, you can already start to imagine how different types of media and how different types of devices make use of different types of communication. All right. So, for example, a telephone conversation is ideally, all right, a two-way communication. All right. Messaging, sending and receiving simultaneously is also two-way. All right. However, TV, for example, might not be two-way. All right. Although even that notion is actually being changed nowadays. All right. Especially with the advent of catch up on television. All right. In the past, it wasn't the case. Nowadays, it's actually moving towards two-way. It has spent a long time as a one-way system, all right. But nowadays it's moving towards a two-way system. A book also a one-way form of communication, and so on and so forth. All right. Now you can all imagine, all right, how communication is very, very, very important, all right, in our everyday lives, and it's very, very important to do what when you're communicating with somebody else. What is the most important thing that should happen when you're trying to communicate with somebody else? What do you think that is?
That it gets to the other end clearly.
All right, and
So
and and not only clearly, not garbled up, not messed up. All right.
yeah, I guess
Um,
that's what I meant is
all right.
clear. Like the message shouldn't come along as blah blah blah, for example, you know.
Yes. So essentially, what you want to do is that the message that you are sending should arrive at the other end pretty much intact. Okay. Probably in these times that we live in nowadays because of COVID and whatnot. All right. It's probably not the first time that you were in some sort of like uh, meeting like we have now, sort of, and somehow the voice of the person who is speaking, in this case, my own voice, would come out garbled on your end. All right. Obviously, what happens there? The communication has broken down. You probably have also experienced this in the form of a game. Have you ever played the telephone game? All right.
Yes,
Yeah. So
of course.
essentially, excuse me.
Yeah, we used to play it as kids.
Yes, but it also showcases how important and how much a message can actually devolve the number of jumps it actually makes from one person to the next. If you take, for example, this sentence over here, I saw Susie sitting on a shoe shine in a shoe shine shop. Where she sits, she shines. Where she shines, she sits. All right. You can imagine how that sentence, for example, all right, um, uh, can literally be transformed. All right, literally by whispering from one person to the next. All right, and in a very similar fashion, um, uh, if unregulated, this can happen to each and every one of our pieces of communication. I was sort of like explaining how, for example, data can arrive from one computer to the next via these different devices. That can, in essence, if not regulated correctly, could also destroy the original form of communication that you're trying to portray. All right, and obviously we need to try to mitigate against this. Now, unfortunately, that is not always possible to do. All right. Um, uh, in fact, there are going to be situations whereby there is going to be some form of miscommunication. In fact, on YouTube, on these two links over here, even on Moodle, these two links are also available on Moodle, just for
Down
the sake of
here.
argument. You can
Oh my God,
actually
shit.
see how miscommunication can
Oh, I
arise
thought you
very, very,
capsized.
very quickly.
No,
All
that
right.
was all in my chair.
Um,
The squeaking was bugging
and
Frazier.
and this idea of
The carpet
miscommunication
is a
is
whole shade
pretty
lighter under
much
there,
one of the main
except
tropes
for
that
those
is
little
actually
black dots.
used within comedy. All right, because one person understands the notion in a different way. In fact, these two links are basically forms of miscommunication of situations that have arrived in comedic teleseries. All right, but again, that the same notion applies everywhere where there is um, a lack of communication or communication that does not arrive the way that it was intended to arrive. Okay. Um, uh, so I would suggest that you take a look at these. All right, they're a couple of minutes long. All right. call it your homework, if you will. All right, there's also going to be a little bit of extra bit of homework that I'm going to be giving you towards the end of this lesson, which also requires you to watch a little bit of a YouTube video and answer a few questions. But that's about it. Okay. So, with all that being said, all right, what I would like to do now is I would like to go through a number of different definitions in order for us to understand what what we're going to be talking about, all right, when we use certain terminologies and when we use certain terms, all right, so that we're up to speed with the jargon, okay? Obviously, if you have any questions with what I'm going to be describing in a moment, please feel free to stop me, all right, and I will try my best in order to explain explain the idea in a more um, in a way that you might be able to understand it. All right. So first and foremost, when we're talking about data communications, the first part of that is data. All right. Essentially, data are pieces of information. All right, which in of themselves have absolutely no meaning. All right. Data has meaning when it has some form of context. All right. So, and when data has meaning, all right, you get what is known as information. Okay. So essentially, information is split up, can be split up, or rather can be transmitted, if you will, all right, via two different avenues. All right. That which is known as digital data, all right, or that which is known as analog data. All right. Now, digital data essentially means that you are transmitting information or transmitting this data, all right, in a sequence of discrete levels of value, all right? Essentially, these discrete levels essentially represent ones and zeros, all right? Whether it be changes in voltages or whether it be changes in the amount of light, for example, or changes um, uh, in the radio wave that is actually being transmitted, and so on and so forth. All right, those could all be used in order to represent ones and zeros. All right, and they are used for every for every computer device that you can imagine. All right, they essentially make use of digital signals. All right, in order to represent something. All right. However, for example, the idea of me talking, all right, the sound that is coming out of my voice, that is not digital, that is analog, all right. It is basically a set of frequencies, if you will, or a waveform that is varying continuously across time, all right. So it is literally continuous information that is actually being sent. Now, the problem with analog data is that it is very easy to be affected by noise. All right, let me give you an example. If, for example, I had a dog, all right, and the dog started barking, all right, that is a form of noise, all right, because at the end of the day, you would also be hearing the dog, which is not really part and parcel of what you actually what you actually logged in here to listen to. All right, if my phone rings, that's another form of noise. All right, and you can imagine, all right, that most of the, if you will, data that we encounter in our everyday lives, all right, is more analog in nature than it is actually digital. What do we mean by this? If you're hearing somebody speak, that is analog data. All right. If you're watching somebody walk across the street, that is analog data because essentially you are receiving literally photons in your eyes, and you're converting that into pictures in your brain. All right. The way that you feel within a room, right? Temperature fluctuations, for example, that is analog because it's constantly changing depending on certain circumstances in and around the environment in which you live. Okay. Air pressure, that's also analog. All right. Wind, and so on and so forth. You get the picture essentially. Um, so
Sorry,
essentially,
quick
yes,
question. But
yes,
how would the dog be noise? Because it's still being picked up by the mic and
yes, of course.
produced clearly. I was thinking more about white noise as opposed to
No,
stuff
no,
we don't want to hear.
there are various different kinds of noise. Okay.
Oh,
So the fact that, no, no, the purpose of this communication of us, for example, being connected here on Discord is for you to hear me. All right, give out this lecture essentially. Yes, and for us to have a conversation when you don't understand something. Correct. So hearing
yeah,
a dog in the background
would be noise
is
for me. Exactly.
it's noise for you. It's noise for everybody else, all right? Because obviously that um, bark essentially would would be disruptive to the communication. All right, it might lead to the miscommunication that we were talking about earlier. So you might have not
Yeah.
heard a little bit of what I was to say because of the dog barking, essentially. All right. So anything that sort of like interrupts the signal somehow, all right, can be considered as a form of noise. Now, there are different kinds of noises I was explaining, so that would probably mean that we would need to define that a bit more in detail, which we are going to. Okay, so that's essentially the idea.
Thank you.
All right. Any other questions so far? All right. Cool. Okay. So essentially, um, what so when we talk about different when we talk about even different devices, um, we can imagine that essentially we are working with sort of like even different types of data that they actually work with. So, for example, if we talk about a telephone um, uh, is trying to send analog data down a telephone line, all right, to another receiver. Okay, um, as of relatively recently, all right, all telephone lines in Malta, at least, have been converted so that they work in a digital way. All right. So what does that mean? It means that the medium that is connecting the two telephones, one to the other, all right, the communication that is happening between themselves is digital. All right. So somehow the telephones that we have, all right, are taking the analog data that is coming out from our mouths, all right, converting it digitally, sending it digitally, and then recompiling it back into an analog signal when it comes to the speaker, if you will. Okay, and that happens obviously two ways. All right, um, but but that was not always the case. All right. In fact, previous previous signals, if you will, or previous telephone lines, literally carried the analog signal, all right, from sender to receiver, all right, in one straight fashion, all right. So there wasn't this conversion, if you will, from sender to receiver. Obviously, that meant that the amount of communications that you can have at any given point in time was reduced. All right. In fact, one of the major reasons why digital signals all right, for telephone are preferred is because you can actually send a lot more down the same line than you would if you were talking using an analog signal, all right? So it makes better use of the technology that is at hand, all right? But it is fair to say that certain devices, all right, would require, all right, conversion from one medium to the next, which is possible to do nowadays. All right, we've talked about this in terms of a telephone. What about in computing? Well, if we look at modems, all right, or the traditional form of a modem. All right, the whole point behind the modem is in order to convert, all right, digital data into analog data and vice versa. All right, so that two computers which work with digital data would be able to communicate over a telephone line, which originally, all right, allowed for analog data. All right, so essentially, each computer, all right, or each device from their end, if they were communicating over the telephone line, needed this modem, which allowed for conversions. All right. Nowadays, the modems that are coming in, or the modems that we have in our houses, don't really act as modems as such, um, rather as gateways to your ISPs as well as routers. All right, nowadays that is the modern form of a modem essentially. But then again, it always depends on what type of internet service provider you actually have, because different service providers use different technologies in order to get a signal into your own home. All right. Um, for people who are using, for example, uh, Go. All right, Go Mobile as your internet service provider. All right, you could have, depending on where you live, all right, you could still be using a telephone line, all right, a DSL line, or you could be using a fiber optic line, all right. That's one way, all right. Two ways, if you technically. If you're talking about Melita, then you're probably going to have a coaxial cable coming um, uh, into your modem, therefore providing you with your communication with your ISP, and so on and so forth. Obviously, different internet service providers exist, and they might have different technologies altogether. So um, all of these different devices can and do make use of different technologies. So sometimes you would need to be able to convert from the technology that is being used in order to provide you with the service, in order so that you can actually make use of that internet connection in your own home or in your own network, essentially. All right. So, um, uh, essentially, when we talk about data communication, what we're really talking about is how we deal with transmission of digital data across distances. And as we were sort of like hinting at, even in the conversation that we were having up to this point, the way that we traverse distances could change depending on the case scenario. All right. So essentially, um, uh, in order to be able to understand this, we also need to understand some other definitions, such as what is a signal. First and foremost, a signal is literally the transmission of data, all right, over some form of communication system. It can be any form of communication system, all right. It can be done via a cable, it can be done wirelessly, it can be done via satellite, radio, it doesn't matter. As long as data, all right, or digital data is actually transmitted across that particular communication system, essentially you're sending a signal, all right. Now, the signaling signaling, on the other hand, is the process at which you are actually transmitting. All right. So, for instance, the way that a wireless router would work is going to be obviously completely different from the way that, say, for instance, a satellite dish would work, or a different way to how a wired network would work. Okay, all of these different um, um, methodologies, if you will, of sending signals, all right, will depend obviously on the medium that you're going to be using in order to send your data. Okay, any questions up to this point?
I'm okay.
Not okay as well, thank you.
All right.
Sorry.
So, um, uh, so another thing that is usually used in order to be able to describe networks is essentially its speed. All right. Now, usually the speed um, uh, that is used, or the terms that is used in order to define how fast a particular mode of transmission is, all right, can be described in terms of either bit rate or what is known as baud rate. All right, bit rate, all right, as the term implies, is the number of bits that you can send or receive per second. All right. However, sometimes, all right, it's more useful to talk about what is known as a baud rate. What is a baud rate? Essentially, the baud rate is the number of signal units that you can send and receive per second. All right. Signal units do not necessarily equate to ones and zeros. All right. Sometimes, all right, you can send more than one bit at a time. Sometimes you might be able to send um, chunks of bits at any given point in time. Sometimes you might be able to send packets. All right, you might have heard of the term packet at any given point in time. And essentially, the baud rate, all right, of your communication device is going to therefore determine the bandwidth, all right, that is going to allow you to communicate with these devices. All right, sometimes it is more important to understand what the bandwidth is going to be, all right, um, because it actually allows you, all right, to identify, all right, um, how many um, how many units you're going to be able to transmit, all right, um, even multiple communications at the same time, all right, over that particular medium, all right. In fact, I talked about the idea of how telephone lines sort of like were converted um, from analog to digital, all right. Essentially, when a telephone line was analog, all right, then that particular line could only host one telephone conversation at any given point in time. Once that um, uh, telephone line was switched to digital, all right, essentially the wire itself remained the same, all right, that hasn't changed, all right. Well, in some cases it has, but not necessarily everywhere. The the medium itself probably didn't change, but what was actually being sent on that line has. All right. Therefore, by doing that, what you ended up doing was you ended up increasing the bandwidth, all right, or the number of telephone calls, for example, that could happen on that same very wire. All right. Now, obviously, with with systems becoming more and more dependent on telecommunications, all right, that bandwidth might have been used up, and therefore we start moving on to other newer technologies, all right, which will allow you for a greater bandwidth, all right. So, for example, we are moving away, for example, from the traditional phone line, all right, that might have also been used in the I don't know, even in the 70s and stuff like that, to phone lines which are now literally being transmitted over fiber optic cable. Why are we doing that jump? The reason why we're doing that jump is because the fiber optic cable in of itself has a bigger baud rate than these copper cables that have been implemented in the past. All right? That's essentially the idea. All right? Yes. Mana. Bandwidth. Band. Yes, they do. That is basically how. That is not um that Mana. Let's put it this way. The ISP, all right, is trying to um, sell you the idea that you're actually going to achieve that particular amount of speed for your own communications, which is all fine and dandy, you know. But the line that is coming into your own home is not a dedicated line. Essentially, once you are going to connect to their infrastructure, you're going to be sharing really and truly, all right, their service with probably all of your neighbors. Okay. So you don't have a dedicated line unless you obviously pay for a dedicated line. But if you pay for a dedicated line, it's going to be very, very, very expensive. But most people don't pay for a dedicated line. Okay. So essentially, what they are telling you is that they are providing you with the capability of reaching so many bits per second. Now, the probability is that you are not going to be making use of that internet signal 100% of the time. All right. You probably be using it in fractions. You know, you're going to be using a fraction of that connectivity at any given point in time. You're not going to be using it all at the same time. Therefore, you would be able to share the line, all right, that they would have with your neighbors in order to um, uh, do whatever you need to do. All right. So essentially, the bandwidth, all right, um, uh, is more a term that would make sense in terms of um, uh, your internet service provider in that case. A bandwidth in your own home would probably make more sense, or the baud rate for your own home would actually make more sense if, for instance, you have multiple computers connected to the same router, all right, and you are going to be constantly transmitting signals from one device to the other, essentially. Do you understand um, uh, this notion? Okay. Are there any other questions, or would you like me to explain it in a different way? Essentially, the baud rate is how many simultaneous communications are you going to allow on the same line? All right, and that usually comes into um, how many because you can send multiple signals, multiple ones and zeros, if you will, at the same time under different maybe frequencies or maybe different lines of communication and so on and so forth. All right, so it's not just literally you receiving a 1 and a 0. All right, let me give you another example. If you so, have you ever taken a look at, for example, an Ethernet connector? All right, how it looks. Usually, it looks like it's 8 actually. RJ45. So essentially, when you look at um, uh, when you look at at an Ethernet cable, you'd probably see, all right, at the bottom that you have these 8 cables. All right. Essentially, what does that mean? It means that you can receive a 1 and a 0 on each and every one of these different lines. All right. That is why, essentially, with an Ethernet cable such as this, all right, with an RJ45 cable such as this, you can actually have a bandwidth. You understand? All right, so that's essentially the idea. The band is over these 8 bits essentially. Yeah. Okay, that's the idea. But obviously, um, um, not every device um, is like this. All right. This is but one form of communication that is used. All right, there are obviously others. All right, and they obviously work in different ways. Okay, so again, if we're talking about fiber optic cable, you might not actually have 5 or 8 literal fibers in which data is actually going down there. You might actually have a lot more, to pull. So it depends from technology to technology. Okay. All right. Right. So, and are there any other questions? Okay. It seems not. So, I already sort of like picked up on this next point earlier. All right. When we talked about the idea of noise. Essentially, noise is anything which is unwanted that can affect the communication in some way, shape, or form. Now, as I said previously, there are various different amounts of noise that you might have, all right, that can come from inside or outside the channel of communication that you can have. Now, um, there are ways and means of mitigating it, and there are ways and means that one tries to remove this element of noise, and but sometimes um, uh, noise is going to be part and parcel of the signal. All right, and even if you try to amplify your signal, all right, you will also amplify your noise. All right. So essentially, what one tends to do quite a lot is to try to find ways of how to reduce the effects of noise as much as possible. All right, this is why, for instance, you would see um, uh, microphones with protective guards around them in order to help them reduce the amount of noise that you would have. This is why you would see radio stations, for instance, in a soundproof room in order to reduce external noise factors. This is why you would probably also see cables with shielding and so on and so forth. But let's first and foremost try to understand the different types of noise that one might actually come across. All right. So there are what is known as physical noise. All right. So when we talked about the dog barking or the phone ringing or the car passing by, that is a form of physical noise. All right. There's also semantic noise. All right. Does anybody have an idea of what semantic noise is? Any idea whatsoever?
It must be related to something if it's semantic.
Yeah, what does semantic mean? What do you think it means? Let's put it that way.
Maybe it's semantic noise. So it's something which distracts you from the actual message because
Okay.
it differs in meaning.
Because it what?
Because it differs in.
Yes, essentially. Say, for instance, I was talking about weed. All right, very topical, considering that legislation has been passed for it. Let's say that I'm talking about weed. Okay.
Okay.
Now you might be thinking, he must be talking about marijuana. All right. Again, given context, okay, I sort of like primed you towards that, but I might have been talking about weeds in terms of gardening. All right. So the same term might mean completely different things depending on the circle in which you are communicating. So that is what is known as semantic noise.
Makes sense.
Okay. So even if you're using, I don't know, this usually happens with acronyms, for example. Okay. Uh, so so at St. Martin's, for example, we actually have a department known as the BEF department. All right, which is the Business, Entrepreneurship, and Finance Department, right? Hence BEF, all right? But if I said BEF to a World War II veteran coming from the UK, probably he would think that BEF means British Expeditionary Force that went to fight the Germans in France, you know, because that was what it was called, you know, so that acronym means two completely different things depending on who you're talking to. Right? This usually happens when you have people talking across disciplinary divides, right? But that's still noise, essentially. All right. Another form of noise is the white noise. All right. White noise essentially being can come from a number of different elements. Usually, the white noise that you would probably associate it with is basically the noise that you might see on a static television screen, or white noise when you increase the gain on a microphone, for example, you start picking up sounds, all right, of the surroundings, all right. That is also known as white noise, all right. Just out of curiosity, do you know how the this type of white noise um, came about?
No. That's a throwback.
Yes. Excuse me. Yeah, it's from a TV. That's a, yeah, that's cosmic background radiation. That's basically the remnants of the Big Bang, of basically the creation of the universe, or proof of the creation of the universe happening on your television whenever you have a detuned television station. Essentially, that's essentially it. All right. Same things happens with radios as well. Really, um, I would have imagined that you would have picked that up, Alex, given your your profession. So good. Uh, excuse me. It's interesting. It's just an interesting tidbit of information. All right. You have other forms of noise, such as impulse noise. To be quite frank with you, having a dog barking, that is probably more of an impulse noise. All right. Having me drop a marker onto the table, all right, that is a form of impulse noise. All right. So an impulse noise essentially is a piece of noise or an element that is disrupting the signal for a very short duration of time. All right. Hence the idea of an um, impulse noise. Okay. You also have what is known as crosstalk. All right. This is one of the, if not the most, one of the more disruptive elements of telecommunication. Essentially, crosstalk happens when you actually have um, electromagnetic induction, usually, all right, that is interfering with other um, uh, with other um, lines of communication, and therefore you get data literally jumping from one line to another. All right, spoiling the communication essentially. All right. Um, uh, this is one of the reasons why, for example, it is a very bad idea to have, for example, data lines, all right, or lines of data for a network, for example, passing by for long periods of or long distances with power lines, for example, because power lines, all right, if not if the data lines are not actually shielded, the power lines produce electromagnetic induction, all right, which in turn could affect um, the reliability of the communication signal that is happening on these networks.
So is that how an EMP works? Like
To
in
a
the
certain, to a
in
certain yes, to a
administration?
certain yes, to a certain extent, yes. Yes, having, for example, a microwave turn on, but um, that is more interference. That's more of an interruption. The microphone, the microwave interfering with your Wi-Fi. The reason why that is an interruption is because your microwave and your Wi-Fi are probably making use of similar bands of frequencies in order for them to operate, and therefore they interfere one another. All right. In the olden days, all right, you would get crosstalk on telephone lines. So you might pick up the telephone without you actually dialing a number, and um, uh, you would actually be able to hear somebody else somewhere else, God knows where, having a conversation with somebody else. That's a form of crosstalk as well. All right. So essentially, you were listening in onto somebody else's conversation because there might have not been enough shielding between one telephone line and the next, and therefore you'd be able to literally hear that information. Now, obviously, it might not necessarily have to happen that way. You could have actually crosstalk, for example, in networks, as I was mentioning. So, which could also have sort of like disastrous connotations, because I don't know, you might have, um, uh, let's say, an alarm system, all right, or a wire that is used in order to detect, for instance, motion, all right, being passed by very closely to power power lines. And whenever, for example, you turn on a light bulb, for example, the impulse of that of that um, electricity flowing through that light bulb would be enough to send the signal via, for example, the motion detector, which will in turn will trigger an alarm. All right, so that this kind of crosstalk could actually be quite disruptive in that sense. All right, you have another form of noise, which is known as attenuation. Attenuation essentially is um, the physical limitations of the medium itself. All right. Let me give you an example of what I actually mean. So, if I um, um, if I turn on a candle, all right, on my desk here, all right, where is it going to actually be brightest? When I am actually close to the candle or when I'm far away from the candle?
Close.
Closer. So essentially, the light that is emanating from the candle is obviously going to be effective to a certain distance, but after that distance, then it's going to be pretty much pointless. If I'm trying to illuminate, all right, a street, and all I have is a single candle, all right, um, uh, then it might not actually be enough in order to illuminate the entire street. All right, after a certain distance, it becomes not as effective. All right. In a very similar way, all right, different devices or different cables or different um, means of communication become less and less effective, all right, the farther away you get from one device to the other. All right, a typical example would be, for instance, a Bluetooth receiver. All right, a Bluetooth receiver will only be useful for signals that are not more than 10 meters away. All right, again, depending on which Bluetooth device you're actually talking about. Similar things could be said with Wi-Fi signals. All right, you would only have a good enough signal up to a certain distance away from the router. All right, you could also have attenuation in wires and cables. All right, so certain cables are only effective up to a certain distance away, because after that distance, then data will actually start being lost. In which case, you would probably need boosters of that signal so that you will be able to send it down the next leg of the journey, and so on and so forth. All right, so that is essentially an attenuation. All right, and we've already talked about interruptions, given what Bridget sort of like typed down in the text channel here. All right, where, for example, an example of which would be the microwave interrupting signals, Wi-Fi signals that are going into your device because they probably are working on similar signals. All right. Another form of interruption would be, I don't know if you remember this, whenever you used to put your phone next to a speaker and you were going to receive a text message or a phone call, you hear and then your phone will start ringing. All right. That is a form of interruption. All right. It's also a form of crosstalk to a certain extent. All right. But um, that's the idea essentially. Okay. All right. Any questions so far?
No, thank you, sir.
All right. Cool. All right. So when we're talking about different channels, all right, that we're using in order to communicate with, um, different these different channels tend to have a number of different descriptors that are used in order to identify, all right, their capabilities. All right. So when we talk about bandwidth, essentially we're talking about the range of frequencies, all right, that are that can be effectively carried by that particular channel, all right. That is usually measured in hertz, okay. Again, when we talk about capacity or data rate or speed, all right, essentially we're talking in terms of bits per second, which is basically the maximum number of bits that can be carried at any given point in time, all right. Throughput is also measured in bits per second, all right, but throughput is essentially the practical maximum number of bits that can be carried upon a particular channel every given second, all right, and that can be experienced by the user. So essentially, uh, if if you had to contact your ISP, all right, to give you a bit of an example, they would usually tell you what your data rate, your maximum data rate is going to be in terms of bits per second. But your actual experience is going to be determined by your throughput, or the throughput that you're actually going to be able to communicate with that ISP. If, for instance, you are unlucky enough to be on a antiquated line that connects to your ISP, then your throughput, all right, is not going to be the same as your maximum capacity, all right, and therefore you'd have a reduced speed on your signal, all right. Utilization, all right, usually represented in terms of percentage, basically is used in order to identify the proportion in terms of time of when that channel is fully occupied. All right, so you would be able to see how much you're actually making use of that particular channel at any given point in time. All right. Noise, in turn, is usually measured in terms of decibels or dB. All right. It is essentially the energy. All right. All right. That is it is measured in decibels because we are literally measuring the energy of the unwanted signals on our channel. Now, we usually tend to try to make sure that our signal to noise ratio is an acceptable one. In fact, signal to noise ratio is usually calculated using this formula, all right, where we have S on N, where S is the power of the signal, usually measured in watts or in milliwatts, all right, and N is the power of the noise, all right, again usually measured in watts or milliwatts. Make sure, guys, that if you're talking about the signal power in watts and the noise power in milliwatts, then you need to convert into watts or convert the signal power into milliwatts. You have to make sure that we are talking about the same, all right, base here. Okay. It's kind of like saying if I had to divide euros with cents, all right. Euros and cents are not the same base, all right. If you're going to divide, you divide euros with euros, right? For example, all right. In the same way, you're either going to divide watts with watts or milliwatts with milliwatts, all right. So you have that that division, all right. So S on N, all right, and you're going to take the log to base 10 of that value and multiply that with 10. That essentially is the ratio, all right, or the signal to noise ratio value that is used in order to understand how much noise is actually affecting your signal, right? Attenuation, since it is a form of noise, all right, is also measured in decibels, all right, and that is usually the amount of loss in power of your signal over a given distance. So you would be able to identify what the attenuation is for a particular device or a particular transmission medium, all right. You would know how far along distance wise you're actually traveling with that particular medium, and therefore you'll be able to calculate your attenuation. All right. Another characteristic that we need to talk about is the idea of delay, all right, in milliseconds. Essentially, the delay is the difference in time between the signal entering the medium and the signal exiting that same medium or the same channel, all right? Now, there can be various different forms of delay. You can have what is known as a propagation delay, all right? So the delay for it to actually propagate through the medium, all right? The transmission delay or a queuing delay, all right? So the transmission delay would be the delay upon which data is actually being pushed into the medium first and foremost, all right? And the queuing delay might be because you might actually have a number of different other transmissions happening at any given point in time, and it needs to wait its turn essentially before it is pushed forward. You also have what is known as a jitter, all right? Jitter is essentially the variability in the delay of a signal, which is mainly attributed to an analog signal, all right, or a real-time signal. Essentially, it is the amount of deviation that you have from the normal distribution of your signal. Essentially, in fact, if you ever try to measure your speeds, all right, probably you've made use of stuff like this in the past. One of the things that is actually being calculated would be, for instance, your jitter. And this device, it doesn't actually show it, but you would be able to see the jitter as well on several devices and so on. Essentially, the jitter would be the amount of delay that you might expect, all right, on your own signal, because no signal is going to be truly 100% live, for example, especially if you are streaming something. So then you might actually get some fluctuation in your transmission at any given point in time. All right. You might have channels which are guided, all right, so um, a wired network is a guided network, all right, or a guided channel, all right. If you're using something like Wi-Fi, that is unguided, right, because you have more freedom in the way that signals are actually propagated. Okay, guided means that you have to literally follow a specific path. All right. Now, obviously, different types of channels can achieve different or can make use of different types of data. As we said, can make use of analog data as well as digital data, but it also can make use of serial data and parallel data. What does serial data mean? Serial data basically means that each bit of data is transmitted one bit at a time in a sequential manner. Parallel data essentially means that a number of bits are transmitted simultaneously across the medium, all right? And you can also have channels which are synchronous and asynchronous. Synchronous data essentially arrives at fixed times, and the receiver must always be synchronized with the transmitter, all right? Essentially, synchronous channel would be, for instance, in live television. All right, nowadays television is also transmitted digitally. All right, so if you are watching live TV, then essentially you are literally in sync. All right, with your service provider, and they are providing live television for that particular channel that you are watching at that given point in time. All right. So that is a synchronous channel. If, for instance, in the same television station, you decide to make use of the backup or the catch-up features, then that becomes an asynchronous channel because the data can arrive at a time which is not essentially synchronized with the transmitter. All right. So you could have those different types of channels as well. Okay. Now, different channels also make use of different forms of communication. One which is known as a simplex channel, a half duplex channel, and a full duplex channel. Essentially, these different types of channels determine how communication is actually going to happen across that particular medium. All right. So a simplex channel is one in which data flows in one direction and not in the other. Okay. Um, can anybody come up with an example of some form of communication that works in this manner?
Radio.
Yeah, radio is one of them. All right. So essentially, radio makes use of a simplex channel for the simple reason that the receiver is passive, in which they are receiving the signal, all right, and then obviously uh, playing out what that signal um, is telling the radio to play out. Essentially, you're not sending data back, all right, to that radio station. Another one is known as the half duplex. So the half duplex channel allows two-way communication. However, only one at a time. All right. So essentially, imagine you have a narrow bridge, all right, and you have one car wants to go to one side of the bridge, and another car wants to go to the other side of the bridge. You cannot cross it at the same time, um, but it can allow cars to travel in both directions. All right. But if one car is going down one direction, it has to wait for the other car to go up in the other direction. Right. And vice versa. So, anybody else can come up with an example of this type of communication?
Walkie-talkie?
Yeah,
To-
walkie-talkie. All right, a walkie-talkie basically allows two people to communicate, or more people to communicate over a particular channel. All right, but they would need to wait for that other person to finish their communication before they can start communicating themselves. If they both press the button in order to be able to talk, then nobody's actually going to hear anything because they're actually interfering each other. Okay, so yes, a walkie-talkie would be an example of a half duplex channel, and a full duplex channel would be one which allows to and fro communication freely and at the same time, so simultaneously. All right. So, typical example of this type of communication.
Telephones?
Yeah, telephone is one of them. All right. So obviously there are others. All right, streaming such as this. All right. Although you could argue it's a form of a telephone communication as well. um, uh, so yes, that is a full duplex channel. All right. Now, um, obviously, depending on the medium, all right, you can have different forms of communication as well. All right, so different devices allow you to communicate in different ways with other devices. Or all right, so the way that you send signals, all right, depends on what medium we're talking about as well. All right, we can talk about a point-to-point channel, we can talk about a point-to-multipoint channel, we can also talk about a broadcast channel. What's the difference between them? So a point-to-point channel is where you're literally communicating from one source to one destination, essentially. All right, so from server to client. Okay, so from computer A to computer B, for example. Now, this could be very simple. It could be using just a wire or a cable that's connecting the two. It could be um, uh, having I don't know, an infrared signal being sent from one device to the other. That is a point-to-point channel. All right. However, you could also have multiple sort of like steps in the way. All right. So, for instance, you could have a computer which is connected via wire to a satellite, which in turn is communicating via satellite to another satellite dish, which in turn is being transmitted over a wire into your next computer. And therefore, you are sending from your source to your destination. All right. That is still a point to point channel. All right. Because essentially, you are sending your data from one computer or from one device, and its expected destination is on another device. Okay. Another form of communication would be the point to multi-point channel. So from one source, you could have multiple destinations. Okay. So an example would be, for instance, a mainframe, which in turn is connected via a number of workstations across a particular link. Okay. Um, so so essentially, the mainframe would be serving all of these different machines at the same time. This communication is a form of point to multi-point channel because there's one source being my computer and multiple destinations being each and every one of your computers. All right, it falls short of a broadcast because people need to actually log into this particular channel in order to hear me talking. All right, it's not the same like I am talking on a radio, for example, because on a radio, anybody who has a radio, the radio receiver will actually be able to tune in to that particular broadcast. In fact, that leads us to the next type of channel. All right, you have your broadcast channel where you'll have a transmitter which is transmitting indiscriminately over over radio waves usually. All right, and anybody within range of the transmitter which has a receiver will be able to receive that signal, decode it, and start listening in onto that signal. All right, be it a TV station, be it a radio station, it doesn't really matter. All right, all of these basically act as sort of like as a broadcast channel. Okay. Any questions so far?
All very clear for me. Thank you.
All right. Now, right, there are obviously different types of channels that can also be used. All right, when one talks about the idea of a baseband channel, all right, essentially what we're talking about is a channel that is being made up or is being used in order to satisfy one signal. All right, as we were talking about in the past. All right, with the older style of telephones, for example. All right, um, that in the past you literally had to, I don't know if you've ever seen one of these period films where you would literally pick up the phone and say, hello operator, connect me to whoever. All right, and they would literally, you'd have these, usually women they would be, all right, in these relay rooms where they would literally rewire and route you, all right, to reroute your call so that you would be able to communicate with whomever you wanted to communicate. All right. At that particular point in time, all right, if you wanted to call somebody else, essentially what you were doing is you were creating a physical connection, all right, a circuit, a physical circuit, all right, between yourself and whoever you wanted to call. Okay. Meaning that you were using up, all right, that line entirely for yourself. Nobody else was making use of that line that you actually had. Okay, that basically was a baseband channel because there was one signal that was going down that particular wire. All right, and it was only used for that particular communication. That is why telephones in that day were particularly expensive, especially if you were calling outside of certain regions, because you were actually needed to book more than one sort of like network operator in order to connect you from one person to the next. Okay. A broadband channel, on the other hand, all right, is a channel that can actually carry multiple signals at the same time. All right. And the way that a broadband channel can actually do this is through the use of what is known as frequency division multiplexing. Essentially, what this means is that the same the same signal will be able to accept multiple signals, even analog signals. All right, where certain frequencies would be sort of like used for certain different channels. Okay, think of it like this. All right, you might use, for example, the higher frequencies. All right, for channel A, frequencies. All right, lower frequencies for channel B, lower frequencies still for channel C, and so on and so forth. And therefore, you would be able to transmit multiple signals across those different frequencies, all right, in order to have multiple different communications with each other. Then you would use what is known as a band pass filter, all right, which would be able to sort of like separate frequency the frequencies that you didn't want in order to be able to receive that particular signal. All right. So if you knew you were communicating over a high frequency, then you would be able to reduce all of the other frequencies and remove all of the other frequencies so that you'll be able to focus on that particular data that you had for the higher frequencies. Essentially, that is the way that you would be able to communicate more or have multiple communications traversing the same wire at the same time, all right, or the same medium at the same time. Okay, it's kind of like how radio actually works. If you think about it, radio, all right, radio waves or radio stations tends to use the same medium in order to transmit the radio signal to your car or to your home. All right. If you think about it, they're all using the air molecules. All right, in order um, to allow you to receive that particular signal. And then essentially what you do when you're literally tuning your radio, all right, is you are blocking out certain frequencies, all right, so that you can tune into a particular frequency and therefore hear that particular radio station that you wanted to listen to. Essentially, that is the way that a radio works in a nutshell. All right. So these signals will be coming through the air. All right. You would tune your radio receiver in order to disregard basically all of the other frequencies that are coming to it, and you would listen to just that one station essentially. All right. Any questions so far?
All clear.
All right. So, um, as we said, all right, you could have what is known as a dedicated channel or a shared channel, all right, as we were sort of like alluding to earlier. All right, if you have a dedicated channel, it's definitely going to become more expensive, but it's obviously going to be more um, uh, more reliable, if you will. All right. However, it's probably going to be less efficient. All right, we talked about this with regards to ISPs, for example. If you buy an internet connection for your home, you are not necessarily buying a dedicated channel. In fact, probably you're not. What you are buying is a service to your home, all right, which in turn is being fed into um, a shared channel, all right, so that you'd be literally sharing a particular channel with probably the rest of the people in your street who have the same ISP, all right. But it's actually physically possible in order to have a dedicated channel, all right. It would probably cost you a lot more, all right, because it will require dedicated infrastructure, all right. But it is supposed to be at least more reliable, all right. And for some people, having a dedicated channel is very, 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 very important. Okay, because it's more secure. However, being more secure doesn't mean that it is actually used more efficiently. Okay. You have channels which are multiplexed. All right, multiplex channels are basically channels which which can allocate the channel capacity to different end-to-end communications simultaneously. All right, and you have channels which make use of switching, which essentially allocates the channel to a single end-to-end communication for a duration of time. Okay, so if we talk about, for example, the old telephone systems, all right, they used an element of switching, all right, so you would actually make use of a particular channel for the duration of that communication, all right. Normal telephones nowadays, all right, make use of a multiplexed system. So you would make more efficient use of the resources of the phone line that you are making use of. All right. When it comes to multiplexing, there are various different ways that one can actually multiplex their system. You can multiplex your system using frequency. All right. So you, as sort of like I was sort of like mentioning earlier, you would divide your signal um, based on various different frequencies. All right, for your communication. Another variant of that is what is known as wavelength division multiplexing. So you'd have signals of different wavelengths, all right, being passed through the same medium, and then you would pick up the signal, um, uh, the signal using the wavelength rather than the frequency. All right. Essentially, the frequency is the amount of cycles. All right. So the difference between frequency and wavelength is the amount of cycles you're going to have per second. That is what is frequency. Wavelength is how the length between the start of one cycle and the start of the next cycle. All right. So if we had to look at it like this, versus wavelength. All right. So if we take a look over here, all right, the wavelength is basically the difference, or rather the amount of the width, if you will, of one entire cycle, all right, from one point to the next cyclic point, all right, the frequency is basically your wavelength over time. Okay. So how many of those cycles you're actually providing per per second? Questions, guys?
Is this used for a broadband channel?
Yes. Yes. Because even if you think about it in terms of radio, for example, if you talk about radio, when you're tuning your radio, essentially what you're doing is you are switching from one frequency to the next. In fact, we use that terminology all the time. If you're listening to Magic Malta, all right, you're using one frequency. If if you're listening to, I don't know, Calypso, you're using you're listen, forgive me, I don't know the radio stations in Malta because you know, I tend to listen to my own stuff. um, but that is essentially how you could actually make use of different frequencies um, um, in order to receive signals. All right. Now, using similar mediums. All right. Wavelength, on the other hand, is yet another another way of how you could actually receive um, uh, receive certain signals. So, for instance, wavelength division multiplexing is usually used with regards to light. All right, light transmissions. The certain wavelengths, all right, of light could actually be blocked, and therefore you'd be able to receive those wavelengths that you actually want to receive at a particular end termination. The best example that I can show you is, so that you have a physical understanding of what the same principle is used with the cyan, magenta 3D spectacles. So, so these, you probably have seen these, yes, in the past.
Yes.
Yes. So essentially, why would you have glasses with one colored lens and another colored lens? Essentially, the idea was that used to make use of images. All right. All right. Such as this. All right. Which were basically two images superimposed on top of each other. Okay. One which had a slightly cyan tinge, all right, and the other which was blue, which was magenta, all right. Cyan is this color, and magenta was this other color over here. So essentially, what you'd end up seeing through your magenta lens, all right, was the cyan picture, all right. So why? Because the magenta color would actually be absorbed, all right, by the lens, and it wouldn't actually allow it to pass through. So you'd only see the portion of the image which wasn't magenta. All right. Similarly, on the other side, on the other eye, you would only see the magenta image, because the cyan image would actually be absorbed by this picture. And essentially, what that meant is that you would be able to see one picture with one eye, another picture with the other eye, and therefore you would get the illusion of 3D. Okay? Now, in a very, very, very similar fashion, you could use filters such as these, if you will, all right, in order to filter out certain wavelengths of light, okay, in order to be able to read certain bits of information, okay. So like that, what you could do is you could send a lot of data down a fiber optic cable, all right, which essentially uses light in order to transmit data across that particular medium. And in order to be able to filter out the data that you require, you would use these filters, in order to uh, receive the information that pertains to you, essentially. Do you understand this notion?
Yes, that makes sense. Thank you.
All right. Um, uh, so these are two different types of multiplexing, all right, that uses, if you will, the properties of the wave itself that is actually being transmitted, all right. However, you could also make use of what is known as time division multiplexing, or TDM. Essentially, what you would do is you would split up your signal into time slots, into equal time slots, and you would say, this for this particular transmission, I'm going to send it under this particular time slot. The other transmission, I'm going to send it down this particular time slot, and so on and so forth. Essentially, so you would be transmitting data by allocating time slots, all right, to each piece of a communication that you want to actually transmit across that particular signal. All right. Now, the problem is that um, uh, if it was allocated evenly, all right, then everybody is going to be transmitting at the same speed, even if you do not require the same amount of transmission. So let me give you an example. If I had a system, all right, or a home network, let's say, whereby um, um, I had three people connected to the network, all right, where one person is watching the internet, watching, sending emails on the internet, okay. Another one is streaming, all right, and another one is not actually using that system, all right, or rather, I don't know, chatting. All right. You would imagine that chatting and sending emails really and truly is not making use of the signal as much as the person who's trying to stream. All right. Especially if they're trying to stream video. All right. So if I had to literally say, all right, I have one time slot for one type of communication, one time slot for another type of communication, and another time slot for the third type of communication, then the video streaming type of communication is going to have the same amount of duration, all right, of um, of the channel as much as the chatting or the emailing is going to have at that particular point in time, which, as you can imagine, is not making best use of um, uh, of the channel at any given point in time. All right. So what you could do is you can make use of what is known as the statistical time division multiplexing. So you essentially would allocate more time slots to users or to communications which are using a higher degree of of your bandwidth, or would need a higher degree of their bandwidth um, uh, in order to make the most optimal use of the channel itself. Okay. At the end of the day, you don't want to have a channel which is being used um, at high capacity for short amounts of time. Ideally, you would need to make use of that channel to its full potential all the time. Ideally, why? Because if you're not using it to its full potential all the time, then essentially the amount of infrastructure that you actually needed in order to provide the service to that location goes down the drain. Okay, is this clear, guys?
Thank you.
All right. So, one form when we talk about networking and we talk about how channels are actually connected together, um, uh, we talk about different types of switching. All right, there are three main different types of switching. There's what is known as circuit switching, message switching, and packet switching. All right, circuit switching is kind of like how you dedicate a particular network, all right, for the duration of the entire communication. Kind of like how the old timey telephones used to work. All right, so you would literally reserve a circuit from sender to receiver for the duration of the communication, and then you would terminate it once that communication has finished. All right, that is known as circuit switching. Another type of switching is known as message switching. Message switching essentially does not really require, all right, that you have a dedicated circuit, all right, from sender to receiver. However, the message, all right, as a whole will be transmitted, all right, across a path from sender to receiver, all right. So I could have computer A trying to communicate with computer B using message switching, whereby the entire message will go via one route. Okay? If I had to send it again, it might go via a different route. But the entire message as a whole is going to be transmitted. Okay? So, ha. If I had to liken it to a particular example, okay? If I if I were to post a letter, okay, from myself to I don't know my mother, okay, at one point it might take a particular route in order to arrive at my mom's destination. All right, so the postman would literally physically take a particular route in order to deliver my letter from point A to point B. All right. If I post a similar letter again, all right, to my mother on a different day, it might they might take a different route entirely. But the entire message is actually being delivered at any given point in time, even if it needs to transfer from one hub to the next, to the next, to the next. Okay. Packet switching is very, very similar to message switching. However, the difference is that with packet switching is that the message can be broken down into various different pieces, and these different pieces can in turn be delivered via different routes, if you will. So, if we had to compare message switching with packet switching, it would be like, I had a jigsaw puzzle, for example, and it was complete, and I send it as is to somebody using a courier service. All right. If the entire message, or in this case, the entire jigsaw puzzle, would actually travel, all right, from the source to the destination as a whole. Okay. However, technically speaking, I could also take each and every individual piece, all right, fire them off and send them out via different routes, via different couriers, and they will all arrive at the same destination nonetheless. All right. The difference between message switching and packet switching is with message switching, the message can be quite large. All right, which might not be a feasible option to have for every type of communication. All right, it's one thing if I'm trying to send a text message, for example, because it might be quite short. It's another thing if I'm trying to send a video, if you will. All right. So message switching might not be suitable for different types of communication. Whereas with packet switching, it might be the case that different pieces of the message might arrive at different times. So what would be very important is that each piece, okay, would actually be numbered, so that you would actually have a sequence in which these pieces are actually would actually fit together. So whoever is receiving them from their end, they would actually need to rebuild the entire message themselves in order to be able to read whatever I send them. If something doesn't arrive, then I would need to resend it. Okay, that is essentially the difference between the two. Is this clear, guys?
Yeah,
Okay.
clear here.
Okay, cool.
Can you perhaps re-explain packet switching, please?
Now, imagine the idea of the jigsaw puzzle. All
Yeah.
right. If I had to send you a jigsaw puzzle, all right,
Mhm.
I can send you. Let's say, imagine I have an entire picture, a big jigsaw puzzle with all the pieces all set already ready. All right. So you have the entire picture ready. You can actually look at the picture and you'll be able to see what the picture is all about. Correct?
Yes. Okay.
All right. If I send it to you as is, so completed, then essentially I would need. Imagine it's a very big jigsaw puzzle. I would probably need specialized containers in order to deliver to you, etc., etc., etc. Yes,
Yeah. Okay.
but it will arrive to you whole. Okay. Now that is one way of going about it, but obviously that meant that I needed to have an infrastructure that allows me to deliver messages of that type.
All right.
So as in DHL or Multipost or whoever needs to cater for me sending awkwardly sized packages to you. All right,
Okay. All right.
right. Essa, as you can imagine, the bigger the stuff becomes, all right, the more awkward this can become. All right, the same thing happens with data. All right, if you're sending text, it's one thing. If you're sending images, it's another thing. If you're sending videos, it's another thing entirely. All right, the files become bigger, bigger, bigger. Yes. So what I can do is I say, all right, screw the idea of actually sending you the whole thing as is. All right, I will send it to you piece by piece. All right. So imagine I had the jigsaw puzzle and I literally was taking off each and every piece. And I was sending them to you individually. Sometimes I might have sent you 3 pieces at once. Sometimes I might send you 2 pieces. Sometimes I might send you 5 pieces.
All right. All right.
All right. But I'm sending you these pieces. All right. But at the end of the day, in order for you to be able to see the picture that I wanted to send you in the first place, all right, what do you need to do from your end? You would need to reassemble it. All right. So I need to
Okay.
give you instructions of how these different packets sort of like connect to each other.
So it's essentially, I think I had a brain fart over here, but it's essentially like the packets that you send, for example, when you're pinging another device, for example.
Essentially, yes, because this is how devices actually send data across the internet currently. This is the
All right.
technology
All right.
that is used. However, you would need to reassemble it. Now, it could be, all right, it could be that there are certain pieces that I send that might get lost within the system, all right, somehow. And after some time, you're going to tell me, "Oi, Isma, my jigsaw puzzle is not complete here. I cannot see the entire message. Imagine the message was actually a picture or a picture of instructions, to put on. There were a couple of pieces that haven't arrived. You'd say, I didn't receive the entire message. Could you resend those pieces that I have missing? You say, okay, sure, and I will send you those pieces. That is essentially what packet switching does on a daily basis when you talk about networks in general. All right, you would I would send these packets out. All right, they might take completely different routes in order to reach you. All right, they might they might arrive at you out of sync. So you might receive
Mhm.
package 10 before package 1 before, and so on and so forth. You would need to reassemble them, and it might be the case that certain packages never arrive to you. But then you would be able to tell me, listen, certain packages haven't arrived. Could you resend them? And I would resend. All right.
All
So
right, all right, all right.
that is basically what package switching is all about. Okay.
Okay, understood. Thank you. Thank
All
you.
right. So, I'm going to stop here for today. All right. What I wanted you to do as homework. All right. We'll continue talking a little bit about this. Finish off these slides. All right. There's only a few slides left in this set. In 2 weeks' time. All right. However, in the meantime, on Moodle, let me just show you here. There is this section. All right. All right, we are currently performing this introduction section. Okay. The next section is networking protocols and applications, and there is this this set of slides called networks and the internet part 1. And this video, essentially, what I wanted you to do is I wanted you to watch the video. All right, there's the link on the slides as well. All right, called Warriors of the Net, which explains essentially this idea of packet switching in a little bit more detail. Okay. And then there are a number of questions that I would like you to answer. So essentially, we're talking about these set of slides. All right. You have this YouTube link to the video. All right. It's a bit dated, but essentially the idea is still the same. All right. Which explains to you what happens whenever you click on a link, all right, on the computer. And then you have a number of questions, all right, that I'd like you to answer yourself, all right, in order to make sure that you have understood what actually happens for data to go from your source to your destination and so on and so forth. Okay, is that clear?
طيب.
All right. Thank you.
Okay.
Yes, it's clear.
Okay, so
Thanks.
I will see you guys in 2 weeks' time. All right.
All right.
Thank you
Okay.
very much.
Thank you. Good night.
Thank you.
Good night.
Good evening.
Thank you.
Thank you.
Bye bye. Don't forget to punch out.
Yes.